Hello and welcome to Metaphysics. I'm Jesse. This video is the second video in a three-part series. In the first part, we went over how you can kind of basically understand the way you kind of break down and rebuild vectors in a different basis, in the hopes that eventually this will lead us to understanding how Fourier series work. So we want to take what we know about vectors, apply them to Fourier series. So in this video, the way that the first thing that we need to do is try to understand how does the top expression, so a dot b, so this is just a dot product between two vectors, how does that relate to this expression here? So this is the integral of two functions f of x and g of x over some interval 0 to L. So this is what we'll see a lot in Fourier series problems. We'll have some kind of periodic function defined over a length L, and we want to break it down into some basis functions, usually sines and cosines, but we can just kind of say f of x and g of x. So we actually want to think about this geometrically, in a sense, or maybe pictorially is a better word. So a and b are two vectors, and so you can kind of think about representing vectors as columns, where you have values at each point in the column for each vector. So a is maybe like 1, negative 0.5, 3, dot, 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 dot. And b is something else. So b maybe is like 0, 5, 12.1, dot, 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 dot. So these two vectors may be represented another way. You could almost think about being some sort of like discrete function. So 1 is maybe over here at 1, negative 0.5 is over here, 3 is way over here, and so on. Whereas b, so this is kind of a pictorial representation. So b is 0, so that's right in the middle. 5 is like off the charts. 12.1 is like even further out here. So you get the idea. And so this makes it a little bit more obvious how we can represent f of x and g of x on this interval 0 to L. Because f of x probably looks something like this. So it's some function on 0 to L, and maybe it does something crazy. And g of x is probably something similar. Maybe g of x is a little bit more smooth. So for each of these functions, we can imagine kind of slicing them into small intervals like you kind of do in like maybe an intro calculus class. So we're going to take some small dx and kind of slice our function like this. And I probably shouldn't have drawn this one quite so crazy. And the same thing with g of x. So we're going to slice this just into small intervals. And so if you start looking at f of x and g of x in this way, on the interval 0 to L, they actually become just a series of numbers. So maybe on g of x, this is like 0.1, then 0.2, and it goes up to maybe 0.5, and then down to minus 0.5 over here. And so a vector is a series of numbers, and in some sense, we can think about discretizing f of x and g of x into also a series of numbers along the interval 0 to L, whereas in the vector case, we just kind of had some number n of vectors here. Over here, we'll have like L over delta x. So like n tilde is going to look something like this. So we take our whole interval L and divide it up into little pieces, and so that'll give us n numbers. So now the question is, well, so how does this intuition relate to a dot product? So for vectors, what do we do? So again, we have these two vectors. So I'll write them a1, a2, a3, dot, dot, dot. B has entries b1, b2, b3, dot, dot, dot. So what happens when we take the dot product of these two things? Well, so we kind of know how to do this. If you have like two vectors like x hat, y hat, z hat, and those kind of components, you know, you take their x components and multiply them. So this would be like taking their first components, multiplying them. So that's a1 times b1, and you add it to their second components and their third components, and kind of so on all the way down the line. This is a2 b2 plus a3 b3. That kind of goes on. So now, how does this make sense for our inner product definition, or sorry, our dot product for vectors, where we're kind of integrating our functions over an interval 0 to L. So how do we turn kind of like this picture here, where we're multiplying numbers from each of them together and then adding them into our integral kind of idea? So let's think about this in a little bit of detail. So let's draw some axes here. So let's say we're living on 0 to L and we have two functions. Our first function is going to be f of x, so f of x will be in red. I'm going to draw these a little bit more simply now, so I can just something kind of, let's say it does something like that. And g of x I'll draw in green. Well, let's say g of x looks something like this. Okay, so now the question is, what is this integral expression look like? What is the integral of f of x times g of x over this interval 0 to L? So kind of from our intro calculus days, we know that an integral can kind of just be represented by a sum of dx times the value of the integrand at various points along our interval. So what we can do is, again, we can think about discretizing this and kind of turning it into a sum. So at each point here, we have, like, we'll say maybe this is f of 0.1. We have g of 0.1 in this little area here. So what we do in our sum for this is we're going to have f of x times g of x at each of these intervals, and then the integral means we actually add them up. So we're taking the product of things, so like f of 0, g of 0, plus f of 0.1 times g of 0.1. And so then obviously we have to do some limiting procedure where we take these step sizes. So instead of 0.1, we have to write it as probably like delta x, and then take some limit as delta x goes to 0. But this thing down here is starting to look a lot more like a dot product. We're multiplying two things, so f's and g's, and then we're adding them at a bunch of different locations. And now our location just kind of runs across our interval rather than running down kind of the shape of a vector. And so in Fourier series, you'll generally find that you'll be using sines and cosines. It's kind of the functions that Fourier series were designed to work with. So let's draw this out. So I'm going to draw sine of x in green, cosine of x in red on the interval 0 to 2 pi. So what a sine of x looks like? Well, this starts at 0, it goes to 0 again, then it goes back up to 0 at the end, and cosine of x starts at 1, goes to -1, goes back up to 1. Maybe we can, the sign is a little bit short on this side, so let's extend that down a little bit further. There, that's a little bit closer. Okay, so now why is it the case that these two things are kind of orthogonal? So the way to look at this is to take, again, just kind of imagine breaking it up. But what we want to see is that, so in this region here, so in the region before this line, here, and then here, let's look at the sign of our functions, and kind of notice, so here it's going to be f of x times g of x, or sine of x times cosine of x. And in this region, they're both positive, so they're going to contribute positively to our function. Here, one is positive, so sine is positive, cosine is negative, so these are going to contribute negatively to our integral. And over here, they're both negative, so this will again contribute positively, and here again they switched, and so here it's negatively. And so obviously this is just pictorial, but you can kind of get the sense that these things are going to sum up to 0. And so our integral of sine of x times cosine of x is going to be 0, which is convenient because in some sense this means like the dot product of sine of x and cosine of x is 0, which means in our kind of like function space, or our function vector space, sine of x is orthogonal to cosine of x. So this is nice. This is something that kind of helps us define a basis in terms of sine of x and cosine of x. And so this is a little bit of motivation for why you might believe, I mean, you could just work through the math and do sine of x, the integral of sine of x times cosine of x, and see that this is actually the case. But this kind of pictorial representation, I think, helps you get some of the intuition. So the other thing that you'll see in Fourier series a lot is different sine functions. So we're going to draw two sine functions. So we'll draw it for n equals 1 on the interval 0 to L, and then also n equals 2. So sine of pi x over L, so that's n equals 1, so that starts at 0, and then by the time x is equal to L, the argument will have become pi. So if n is 1, if x equals L, this thing will just be pi. So this means our n equals 1 sine function is kind of like a half wave. Let's draw this. And what about for n equals 2? So the red curve. So if n equals 2, as x goes to L, the argument will become 2 pi instead of just pi. So this means the sine function goes through kind of the full wave. So let's see if I can draw this. Okay, and so again, let's kind of do the same process that we did before, where we divide this up. This case is pretty simple. We kind of only have one division, so over here they're both positive, so they're going to be positive, and over here they're both negative, so the function will be negative. And here it's a little bit easier to see. Okay, so the sine function, or this half wave, is kind of symmetric along this side and along this side, and then our full wave is also symmetric or anti-symmetric from that side to that side. So it's a little bit, maybe a little bit more clear that these two functions are actually orthogonal. And it'll actually be the case that these functions are orthogonal for any n you choose. So n equals 1 and n equals 2 is not a special case. As long as n is a positive integer, you can do the integral of sine of n pi over x times like m, so n and m pi over x, those two things multiplied. And as long as n is not equal to m, the two functions will be orthogonal when kind of the dot product that we're defining is on the interval 0 to L, and it's this integral in dx. So if I choose n and m, as long as n is not equal to m, these two functions will be orthogonal. But if they are equal, again, we'd kind of want the dot product of something with itself to be 1. So as long as we normalize these things correctly, that will also be the case. So this is why, in addition to having sines and cosines, you also kind of need multiple sines and multiple cosines. So this winds up giving you kind of like a complete orthonormal basis if you choose all the sines and all the cosines with kind of this as their argument. All right, so that is kind of some intuition for why you kind of wind up defining the dot product for function as the integral over some interval. So next time we'll be going over a couple actual problems using Fourier series just to kind of see how these tools work out.